Lecture 3, MFGE422, Flow Analysis and Simulation. We'll be going through Chapters 5 and touching briefly on Chapter 15. Okay, Chapter 5, Objectives. We're going to understand the importance of material flow and flow analysis and go into a little bit of that. Identify, construct some various flow analysis tools, and then I'm going to introduce to you the idea and concept and actual document known as the standard worksheet. All right, so I think this is on page 117. That's what I have there anyway. I've got a couple of pictures here of product versus process orientation in a facility. And the upper viewer there, 5-1A, process flow. So what you see here is a manufacturing facility. It's sort of set up as a job shop, right? It's set up to have maximum flexibility with respect to the equipment that it has to run. And you're going to be hopping back and forth between different operations depending on what job shop what job shop you've been contracted to do. So you'd see this typically in a lot of small aerospace companies, contract manufacturers, that sort of thing. The deal about this, though, is that it's not super lean. There's one of the areas of focus in our class, and the areas of focus in manufacturing engineering in general, is to reduce the waste. And you can see here each of those lines that go from one spot to a next. Those long leader lines going from the clean to machine 3 and back over to weld. Each of those long lines represents what? It represents walking, represents transport, represents probably WIP. I'm sure it represents a large batch size. Batch sizes bury issues, quality issues, and now if you have a mishap, not a one-piece problem, but a 450-piece problem. So while you can get by as a job shop, many garage band type places do, most of you will likely work for companies that are not garage bands. Most of you are going to work for companies that are larger in nature. They're going to run more of the product flow layout, where you're going to have something set up from one step to the other, one operation to the other. Likely it's cellular based, likely one piece flow. We'll be focusing on that methodology, your projects, your lines, your manufacturing facilities you're developing, the 3 or 2 products your company's going to launch. They will be focused in a product-oriented facility, not process. Process is bopping back and forth, right? Product-oriented. Now, we also said that maybe you'll have a shared process amongst your lines, that whole example of the paint line, all right? All right, that's cool. Then you'll have a mix between product and process-oriented, because, again, we're not going to buy 3 paint booths. You are seniors about to graduate from engineering school, right? So product versus process, again, material flow in a product-oriented facility obviously flows much better, much smoother, distance is less, we talked about that already, less confusion about where things have to go. Clearly, if you're in a cell, it's obvious, point A to point B to point C, out the cell, right? But again, if you're a job shop, you can't necessarily do that. The thing about process-oriented designs, right? Because you're in a job shop environment, you're going to have a setup. You're going to run this lot through maybe a 5-axis machine, and then the parts are going to come off the 5-axis machine, and they're going to go out to an anodized operation. And they're going to come back from an anodized operation. They're going to go back into another 5-axis machine. Right? Each time you do that, it leaves the facility. It comes back for another anodizing and machining step. You might have one piece of equipment that is whip, zip, fast. It's going to be an expensive machine. Maybe it's palletized. There's some infrastructure behind it. You're going to have CNC measurements. I know a few of you know what I'm talking about, right? The deal is there's risk, right? You're producing WIP. You're producing defects. You might have an operation that goes into a machining, like I said, comes out, goes into anodized, and it comes back, and you begin to machine things, and all of a sudden, you're machining it wrong. What have you done? You've just ruined a bunch of parts that have already been machined once and anodized. And oh, by the way, now your contractual obligation for an on-time delivery is at risk. It's a tough way to run a business. You can do it, but it's a tough way to run a business. Product routed, most of the companies you'll be working with, one-piece flow, cheaper machines, often little or no automation. The nice thing about it is WIP is suppressed and defects are covered before they go on to the next operation. One last view. This is an example of probably got too many slides. But anyway, again, your plan's going to likely look what's going to be happening there on the right-hand side. Unlikely you're going to be a garage band on the left. Process versus product. At this point, everybody should be really crystal clear about the difference. As if you haven't heard enough product-oriented propaganda, yet another slide. Lucky you all. Okay, so item 1 here, simplifying coordination, first in, first out, right? Solving problems rapidly. Again, one-piece flow does this. This is, again, probably one slide too many. Maybe I'm at 2 slides too many. Experience less work in process, eliminate excessive handling of materials. And we do see that, kind of a theme, right? The length of the arrow, the distance of that arrow in a process-oriented facility, that transport has got a bunch of stuff buried behind it. WIP, distance, carrying, material handling, the risk of failure. And what's interesting to note is when we go into our simulation really looks at the length of those arrows, the efficiency of our layout. And we'll see tonight a couple of methodologies where we can begin to tease out how it should look to be most effective, even before you step into the simulation. Where am I at here? Number 5, fix quality problems quicker, one-piece flow again, support flow of operators which could be standardized, and of course, less floor space. And I'm going to say most of the time. I mean, you might be able to shoehorn a bunch of equipment into a small, rickety facility, and then when you walk in, you just see mountains of inventory, mountains of WIP, and nobody's communicating. So you can run a business that way. You can even make money that way. But again, most of you won't be in organizations like this. But if you are, the tools you learn here will be equally applicable. There's a lot going on in this slide. So the first thing I want to point you to is this process manufacturing sequence chart thing. It really is, it's called a manufacturing sequence chart. That's sort of the block flow diagram. Now, in your book on page 136, they're going to show you an operations chart. And they're going to show you on page 128 a process chart. And then on page 138, they're going to show you a process flow chart. Each one of those charts is sort of a different way of looking at a manufacturing operation. Some of them are a little more complicated than others. They serve different purposes. For your project, notice Project Doc. Project for you, you're going to use a manufacturing sequence chart, which is what I'm showing you right here. You have a series of components. Let's just look at that upper left-hand box. You've got a series of components, a probe, a remote light, a grommet, right? Those pieces are all coming together, being assembled with various steps, and then out, basically we're pooping out a housing of some sort, of a control housing, right? There's some power cables that are added on afterward. What's going on in that box in the upper left-hand corner is essentially a cell. And you see the cell pictorially. And now the process steps are different. I didn't go take the time to make the little graphic up in the upper right-hand corner match exactly what's going on in the graphic in the left-hand corner. Bad me. But anyway, you get the idea. It's a U-shaped one-piece flow cell. Parts coming in step by step, and out they poop to the next operation. It says customer. Customer in this case is place wires in the control module housing. That next box on the way out that's left, that golden sort of quadrat that's in the corner there. I also want to point out to you, in the lower right-hand corner, a representation of the operation that's going on in those two views. What's going on in the manufacturing sequence chart, you can see there pictorial, it would actually look like the cell, kind of a bird's eye view of the cell. Those two things come together with facts and figures and numbers in the standard work combination sheet, the cell load chart. You will be producing a standard work combination sheet. I have an Excel spreadsheet that you can have and use, so free of use. I'm not going to say, you plagiarized me, because I'm giving you the darn thing. But I want you to use that format. That will be what you provide for standardizing how your manufacturing line, or if you have multiple cells in your line, how those cells will function. What the actual employees on that manufacturing line will be doing. And we'll go about, well, I'll show you later. There's another lecture later on how it shows you, I think, how that actually works. We'll step through that. It's a later lecture, but just rest assured you'll be responsible for a manufacturing sequence chart. That's the box in the upper left-hand corner. You will be giving me a diagram, diagrammatically, you know, probably with not little ovals and whatever that is, it's a hexagon and a funky, you'll be actually plunking down pieces of equipment, right, in an actual diagram of a cell. You'll be giving me that, right, and you'll also be, this is individual work, right, each of you, as part of your project, will be providing a manufacturing sequence. Each of you will be providing some kind of view of your manufacturing line or cell. Each of you will be providing a standard work combination sheet as part of your manufacturing line. So again, Project Doc! Exclamation point. All of your cells, your manufacturing cells, will run counterclockwise. That is a standard element of every lean manufacturing cell. Counterclockwise process. So it goes from if you're in the cell, the parts are running from your right to your left. I have a little graphic here, little like almost like a sweeping counterclockwise arrow. I want you to tattoo that into your brain. That's some body ink. That's some ink for your brain. Every cell needs to run this way. We're going to see a number of pictures from Kiyoshi Suzaki and his new manufacturing challenge. Suzaki was a really sharp guy, very smart Japanese sensei, but for some unknown reason, all of his cells are running in the opposite directions. We're going to have to look at those and say, why did he... Now, and there's a question too, right? Why? Why from right to left? Why counterclockwise? And if we were meeting in class, there'd be a pregnant pause where I would wait for an answer. But I can't because you're not there. You're, wherever you are, and there's no interaction, which is a total bummer, but it's the way it goes. So, what I will tell you is this. If I were to ask you all in the class to raise your hand if you were right-handed, 80% of you would raise your hands. I would then ask how many of you are left-handed. And probably 40%, no. The remaining folks are obviously left-handed. Now, I do a sobriety check to make sure everyone votes, because sometimes you ask a class a question, and everyone kind of sits there and stares at you. But you guys never do that. You're always so interactive with me, and I so much appreciate it. David Matsumoto, he's an author, lean author. He actually went and looked at some studies. Now, I have never actually experienced this myself, right? But he says there's a reason why every track in the world runs counterclockwise. Think about it. Every running track that you've been to, which direction does it run? Again, counterclockwise. Why is that? I guess somebody somewhere, I don't know, the Greeks, the Romans, I don't know, somebody somewhere measured success, measured running success, and they found, for whatever reason, right, that you ran more rapidly going in a circular direction, counterclockwise, than if you went clockwise. Now, I don't know this for a fact, but I do know that when you're in a manufacturing cell and you're right-handed, the best use of your ability to grab a part and place it in a fixture happens with the hand that you have the most dexterity. So in a lean one-piece flow cell, you grab the part from your right-hand side in your dominant, highly agile, highly abled right hand, and you're able to set that in the fixture very rapidly. In fact, if you were to naturally do that, that's how you do it. After you've hit the palm buttons and the machine goes, right, and head lifts up and the gate lifts up, it's very easy to take that part with your left hand and push it down the chute to your left, right? That's easy. It's like grabbing a coconut and throwing it away. You can do that with your left hand. It takes no dexterity. In fact, A super user, right, is going to be taking his left hand, not even looking at the part. It's just going down the chute. The next operation is already with the right hand and the part in the nest. That's why cells run counterclockwise, because most of us are right-handed. Most of us are going to grab the part with our right hand, put it in the nest, and push with the left. I think, too, right, that your left leg versus your right leg. Your right leg is stronger than your left leg. It just is. I don't know why. It just is. Why are our brains like this? I have no answer. But if you think about this, when you're running around a track, half the time you're running around a curve. Half the time you have to push off with that right leg around a curve. You want the power on the outside leg, shove it. It's like the wheel. It's like the outside wheel of the car. You want that man pulling you around the corner. So it makes some sense, right, that when you're running clockwise, the weaker left leg is not going to give you the same level of power. So that's why I think tracks are counterclockwise. But I know for a fact that's why manufacturing cells run counterclockwise. So here is a manufacturing line, and it's got a lot of conveyor in it, a lot of automation. So how many operators do we see in this line? I count 1, 2, 3, 4. I count 4 operators. And I see a bunch of automation, conveyors. Can these operators see each other? Do they have the ability to communicate with each other? I mean, the folks between machine 1 and machine 3, maybe they can across the conveyor, but those two folks absolutely cannot communicate with operator there at machine 7 and 8. And the inspector, if he's finding a problem, how does he tell operator 1, yo, I found a problem. Yo, there's a problem here. Ergonomics, right? I don't even know. I mean, how can they help each other out? If there's a problem, how do they manage that? And then we talked about before, while you have conveyor and you might convince yourself you've got a highly automated, fantastic line, really what you have is probably a bunch of whip, right? You have a bunch of machines pumping stuff out. Maybe it's one-piece flow, but one-piece flow down a long conveyor like that, well, maybe that's the right thing to do. I'm not going to argue with it since you're going to be in an automation class. You smart folks will figure that out. But in this particular case, there's an awful lot of equipment here that's non-value added. Conveyor is non-value added. Parts sitting on a conveyor are that's whip. That's non-value added. Lots and lots and lots of waste. Now maybe because operation 6 sitting there, right, is a machine that runs wickedly fast but has lots of downtime. So what that would mean is you'd have to have a bunch of whip ahead of it, right? So that when it's running, it can run like crazy and drain the line. And then when it has a problem, and the machine goes, and the andon light goes on, the guy standing right there at machine 6 goes over and clears out the nest, right? While he's clearing out the nest and farting around, the conveyor's filling up. Okay, that is one solution. It's not the best solution, but I have seen it work. I've seen it work in high volume environments where pieces of equipment are finicky, they have downtime, but when they run like crazy. So that's one methodology. It typically costs a lot of money to have a lot of installed capacity like that to be able to cover for downtime. That's one methodology. So now we're going to slide that box over. We see now a cell. How many operators in this cell? 2. Can they see each other? Yes. How do they communicate? Yo, I got a problem over here. Can you give me a hand? What about ergonomics? Well, I can't talk much about ergonomics, but I can tell you one thing. The whip is suppressed, right? So now I went from a highly automated, maybe, heavily on the conveyor, lots of whip. It's the same equipment. It's just designed and placed differently. So in such a way that it's now down to one-piece flow, potentially, or at least small batch sizes. Operators can help each other. Too few people, and the question is, where did they go? Well, are they gone? Are they gone? They fired? Well, maybe, but likely what happens is there are other things in the facility that are not being taken care of. There are probably quality metrics. There's probably health and safety issues. Remember, QDIP plus QDIP. Safety first, then quality. Those things, while companies say they're most important, are often things that people struggle with covering. If you can open up the facility, in terms of manpower availability and have them focus on health and safety and quality issues, that is profound. That is profound. That's sort of our job as manufacturing engineers, to try and get people in the right spot doing the right thing that adds the most value. So that before and after I showed you is tabularized here. Assume it was a Kaizen event, right? And now we went from 4 to 2 operators, pieces, whip pieces, dramatically improved. I'm not sure what that is in terms of a percentage, but it's huge. It's like, what's that, like 900% or something like that. Floor space, whacked. Conveyor feet, gone. No conveyor. Sorry, you conveyor people. We got rid of your conveyor. And number of benches, those benches that were in the previous, so that long conveyor thing, right? Those benches are a place for, they're like a flat surface where whips ends up sitting, or crap ends up sitting. Get rid of the benches, you get rid of the whip, you get rid of the crap. So before and after. Now again, you see the picture here. It's you can see the numbers, right? The arrows are going in the wrong direction. Don't worry so much about that. Can we fix that next time? Oh, let's fix that now. Let's spin that around. There we go. Spin it around there, and now it's fixed, going in the right direction. So here is a mixed model cell. A mixed model cell. And in this cell, there are 3 product families being produced. And what you can see here is not every product goes through every step. We look at the cell, and what's the first thing we notice? Uh-oh, there's the brain ink then, the arrow telling us we're going in the wrong way. Wrong way! Let's fix that. Okay, there, let's go the right way now. All right, so now, you know, even we're doing the best we can. Again, it's going the wrong way. I get that. Just let that rest. Let's move on. We've already been through that. All right. The piece here I want you to understand is that while you have a particular cell with equipment, not every part has to go through every process step. Again, that's called a mixed model cell. And this is a U-shaped mixed model cell. And you can see the process steps across almost like in the X-axis. And then on the Y-axis, the product family. And you can see the data points as the part goes from step 1 to step 2 to step 3. The thing I want you to also note is everybody here is playing well. There are no reversals. In other words, when you go from step 3, everybody that goes through step 3 goes on to step 4 or higher. Right? That's not always the case. In fact, the example we're going to see that's going to be in our book and that we're going to work with a little bit tonight, or today, or whenever you listen to this video, is when you have a reversal, what do you do? How do you deal with that? We're going to go into that in some detail. So in our book, turn to page 119. 119, everybody. What we have here is a from-to process routing. It's sort of the beginnings of the idea of from-to. And we're actually going to use this from-to methodology as part of Layout IQ. We're going to eventually get there, our simulation software. But right now, this is sort of the ancient, well-worn, hand-tooled, standardized way of addressing it. Back when knights were bold, and I don't know how it works, men were tough and women were tough too. So we were all tougher back then, right? What I have here are what I'm calling process codes, and they're the same things that are in the book. A is a cleaning operation, B is machine 1. I'm just arbitrarily A, B, C, D, right? Paint, machine 2, machine 3, R for receiving, and S for storage and shipments. So not exactly alphabetical, but see. All right, so, and you can see here, it's sort of what we saw in the previous slide, where you have in the X-axis, you have the routing, A, B, C, going across the way. And on the Y-axis there, you have it by part number, sort of the part number domain. So you have process routing in the part number domain. That's actually how you'd say that. What's interesting to note in this example is that things aren't running quite as smoothly as they were in the previous example because we have what's called routing reversals. So when we start our receiving and we go to step A, part number 1, there I'm on part number 1, folks, part number 1, we go from A to B, right, and we go to D, then we bop back to C. They say, well, what do you mean bop back? You were arbitrary in the first place. How could you bop back? Fair enough, but look what happens for part number 2. Part number 2 starts at B, goes to D, and then on to C, all right, and then comes back to A. So and no matter which way you slice it, right, no matter how you've laid out your process steps, that's a reversal, right? Part 1 and Part 2 are running differently in the cell. Not only are they running differently, something went forward and they had to take some steps backward to keep going. That's a reversal. You will unlikely encounter this in your cellular environment. You are unlikely going to have a mixed model cell. But this is, again, this is classic manufacturing facilities planning. This is like I need to teach you this so you were aware of it. Because this is the good stuff or the tough stuff. It's that foundational element that it's like calculus. You ever going to use it again? But you sure as heck are going to use the algebra that went along with it. All right. So that's what's going on this slide. All right. So now we're going to take a look at this in a sort of a different way. All right, so you saw my sort of arbitrary A through B and R and S. And now we're on to page, let's turn to page 120, 121 in your book. Now this string diagram is what the book calls, or is what they call a string diagram. Cell layout slash, I call it a cell layout, they call it a string diagram. This string diagram methodology is like the classic methodology for sorting out how to place manufacturing steps in a manufacturing operation. This is the ancient, well-worn, hand-tooled, leather-wrapped, methodology that goes back to, I don't know, Middle Ages, Middle Earth, Middle something, way back in the misty green panes of history. But it's classic. So you're going to learn it here. It's kind of like calculus, right? I mean, after you've learned calculus, how much do you really use it? Yeah. But you darn sure use the algebra that you had to learn to make the calculus crank turn, right? This is sort of similar to that, but it's not quite as painful as calculus, all right? But it's the idea you're learning the classic methodology, which helps you understand foundationally how to take steps forward with sort of more better techniques. More better. Nice. See, I am an engineer. All right, so what you have here is we're starting with R, receiving, and ending with S. Consider that your backbone. Receiving and shipping. Receiving, and then just alphabetically A, B, C, D, E, F. It's arbitrary. I already arbitrarily number the darn things. The book that your authors did as well. So we're just going to go A through F. Just lay them out. Those are process operations laid out. If you can imagine a cell, and it's not necessarily cellular, but a cell, or they're a straight line something. It's independent of the footprint. And we'll see that footprint actually makes a difference later. But right now, just in your brain, just see this backbone. Now, as process steps go from A to B to C to D, right, in your process, in your part domain, right, as you're going from left to right, those are all on top of the backbone. The green arrow, those are all going from left to right. That's on top. Stepping through one after the other, right? 1 foot ahead of the other. Underneath the reversals I talked about, right? That's also known as AKA backtracking. Going backwards. So that goes underneath. So forward goes on the top, underneath goes on the bottom of this backbone that starts with S, starts with R. Now I'm really confusing you. It starts with R, ends with S, and it runs A through F. All right. So what I have here then is sort of a picture of what's in the book, and then you can see over there on the lower left-hand side the parts domain, and then you see number 5. We're going to focus on part number 5, only because it's got the nice little X's on it, and it's easy to see. The rest of them, I don't know how you, but anyway, the X's are easy to see, right? So we're going to follow part 5. Part 5 comes into receiving. It goes to process C, then A, then D, then S. This would be ARCADS. ARCADS! We're going to follow the process flow for part 5, ARCADS. So it comes into R, and it pops over to C. And as it pops over to C, it goes over from R, it bypasses A, it bypasses B, and lands on C. But we call those steps. Those are steps traveled. they aren't necessarily footprints, but they're steps in this little process map. So from R to A is 1 step, A to B is 2 steps, B to C is 3 steps. So that first Xed line, part 5, goes from R to C. That's 3 steps forward, right? And then it goes from C back to A, the backtracking, right? So that's 2 steps backwards. 2 steps backwards, right? Then it goes from A over to D. That's going again 1, 2, 3 steps forward, and then from D to S, 1, 2, 3 steps and out. Right? When we look at the total number of steps for each process, I think if we were to count number 11, it'd be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Did you follow that? Take the time. We'll go through it again. All right. So from R to A, B to so the first hop from R to C is 3 steps. So I'm going to put your finger on the screen. Step 1, 2, 3. Right. And you're going backwards from C to A, 2, 3, 4, 5. Right. Now you're going from A to D. So that's 5, 6, 7, 8, and then from D to S, 8, 9, 10, 11. There's your 11 steps. So it took 11 steps to pump out part 5. Part number 1 has 9 steps. Part number 2 is 13. If you can follow the bebopping around, great. This layout also has 8 backtracking steps. Now, the book goes into something that's called efficiency. We shall now calculate the efficiency of our initial layout, of our string diagram, and our jump-off point. And they came up, you add them all up and you get 67. So where's the 35 come from? Where on earth does the 35 come from? Well, if you were to run from step R to step S, right, let's count how many steps straight through that is. So that's 1, 2, 3, 4, 5, 6, 7. That's 7 steps. If your part went from A to B to C to A, it'd be 7 steps, moving out, right? That's perfect. And you have 5 parts in the process. Right? If all 5 parts that you were making went from R to S from A through F, 1 step each time, no backtracking, right? That would be a total perfection of 35 steps, right? So that's the perfect process. But we had 67 steps. So our efficiency was 52%. All right, well, great. And you can get the idea. We're going to play some shuffleboard here, shuffle things around, see if we can improve that. But I want to point out one additional little bit, and that is that little sort of mini table I have in the upper right-hand corner. And you look at the high travel processes, the process steps, the high travel sort of direction. C to D, there were 5 C to D trips. A to C, there were 5 A to C trips. D to S, there were 3 D to S trips, and then B to D had 2. So if you were to sort of set this thing up, S is going out the door, right? C to D, A to C, and D to S, you might begin to see that I might actually put them in terms of A first, somewhere in this process loop, and then it would go from A to C, and then from C to D and D to S. That sort of like high traffic, high volume process step might be a way of helping reduce the overall steps and improve my efficiency. All right, next slide. And we see, eureka! It went, we got A, C, D, S, just like we talked about. We can do the bopping around again. If we were to follow part number 5, our CADS, our CADS again, we'd see that we went from 11 steps to 9. So the sum total, we reduced it by shuffling the board. Now we're going from R to B, E, F, A, C, D, S. Right? We've shuffled the deck chairs a little bit. We improved our efficiency to 61%. All right. Okay, that's fine. So this is the way the book teaches you. Basically, you have to sort of like rearrange the shuffleboard chairs and then do the math again. Rearrange the chairs again, do the math again. And what I'm saying, well, you could, by inspection, you can kind of start getting close. And here's the point. By inspection, you can kind of get close. And that's really what we want to do. We want to have it the simplest, straightforward way of sorting this thing out. We're going to see that in a moment. So make sure you're all on page 123 in your book so you can see this. Cell layout from 2. So we have our part domain, we have our routing operation sequence, and then we also have in the part domain now, table on the bottom, we're looking at in the part domain the total weight shipped, right? And relative importance based on total pounds shipped, total weight shipped. And what you see here is part 4 and part 2 are the high runners based on total weight. Based on total weight. All right. Not always, though, is a manufacturing operation that wrapped up in total weight. But in this specific case, it is. And the example in the book says, well, then if it's by weight, it's sort of your volume throughput, you want to weight those parts, weight part 4, and no pun intended here, weight, part 4 and part 3 as more important in terms of laying out your line. So turn your crank some more and check out your efficiency, and then go ahead and plop it out on your manufacturing floor. That's sort of the way the book handles it. I'm going to show you something a little different. Let me show you something. So the methodology I'm about to talk to you about is not in your book, but it is absolutely a lean tool. It's called a PQPR analysis. So if you Google that, you Google PQPR analysis, you will see all the lean sites, LEI and the rest of them, they're going to step you through a PQPR analysis. This is how most of us do it today. We don't do the, hopping around thing. There's some element to that. We start with PQ, which is product quantity. Now, in the case of the example, they had quantity in weight, all right? But typically, what we're going to look at in terms of product quantity is the unit volume or the sales price or the revenue for product lines. So on this first graph here, we're looking at the unit volume. This next graph, which really echoes the first graph, we're looking at sales dollars from this particular line. But we're going to focus at this point just on product quantity, PQ. And you can see here, part number 4 and part number 3 are the majority of what this cell has to produce. The majority of it. Not quite the 80-20 rule, but it's not that far away. All right. So you really are going to want to focus then on part 4 and part 3 in terms of the routing, and let the other parts sort of not really fly around in the breeze, but you for sure want to improve the throughput of part 4 and part 3. That's the biggest bang for your buck. That's what you want to focus on. So that's the PQPR analysis. The first step in that is listing all of your part numbers, the volumes, the unit volumes, the sales price, and the sales dollars. So unit sales, the price of what we're selling it for, right? Our revenue per part is the total sales dollars, right? Because some parts you might have a part that it sells for $1,000, but you make 2 of them. Well, okay, so you're really not going to want to go by unit sales. You're going to want to go by sales dollars. But there are instances, right, where a manufacturing operation, maybe you're selling something for a wicked high price, right? And you don't sell that many of them, and you say, well, you know what, my profit margin is so good on this thing, I'm not going to let it drive the direction or the process routing, because I can live with that. So I'm not going to do it in sales dollars. I'm going to do it in unit volume. So you make this choice, right? You make the choice. And typically it's a choice that's done not by you alone. Typically it's done by plant leadership. But you're going to be a person of interest, in terms of helping solidify the numbers, solidify the data so that your leadership can make the right call. So here's the other half of the PQPR. It's the PR portion, the process routing. We're back on our old process routing from our book. Golly, interesting. So, and you can see here I've sort of reformulated it a little bit. So it's what's in your book is on the top of the page. And what I've done is I've put it almost like in blocks in an Excel spreadsheet. So I can begin to see sort of how things are laying out step by step by step. It's not all kerned funny like it is on that table in the book. It's more regimented. It's still in the part domain. It's the process routing sequence in the part domain, right? But it's a little easier to sort of get at. Those are the process routing requirements in the part domain for each part. So we're looking again at the process routing, and I'm laying on top of this, that's the top, the sequence, and now we're laying on top of it, basically, the product quantity. So we begin to see sort of this, number 4 and number 3. So I've rearranged in the part domain, I've rearranged sort of the spreadsheet thing there, the cells, whatever you want to call them, right? My little diagram. I've rearranged it so part 4 is on the top, part 3, so they're rearranged by level of importance, by unit volume level of importance. The top one being part number 4, the highest volume, the highest dollars, that's the most important, that's the main line I want to try and achieve, and then I'll step in all the way down through to part 2, which is the lowest volume. So I've rearranged it in terms of the PQ, they've rearranged the PR in terms of PQ. So now we have the PQ-PR analysis. The PQ-PR analysis. And I have that's sort of that same diagram. And what I've done here is I've begun by inspection. I haven't changed the routing sequence exactly. I have a little bit, right? But by inspection, I've got to begin to look at where are my highest volume, highest traffic areas. We talked about that already. There was ACDS. So if I've arranged my cell, the line down there, the maroon and tan sort of boxes down there, I've aligned myself, right, to manage to run that line, ACDS as I found before. I look at the front of the bind from receiving, and as I sort of looked back and forth, I saw, I see that line number 4 there. It doesn't have B in it. F is super important. I want to flow that through as easily as I can. F, A, C, D, S, and then look at that. Part number 4 is going from A, from R to F, A, C, D, S. No reversals. That's my main line. That's my backbone. Right? We also see part 3. Right, part 3 also has ACDS in there, like we saw. So why wouldn't I have that be the same thing? So basically, at that point, that sets the back half of the operation, the back half of the line. Up front, it's all, at this point, it's simply a compromise. It's simply a compromise. You might decide a different routing, for the line in total. This is what I came up with. And, by the way, I knew the answer because the book had the answer. But in general, right, I didn't go through all the efficiency numbers and playing the game multiple times. I just sat back. I took the information from the volume information, right, the PQ analysis, looked at the PR, the process routing, pasted those two things together in a format, that tabularized format, right, that enabled me to see things for what they were. Put them in terms of most importance, and then begin to set the line up by inspection. That's how you do it. That's how you run a PQ-PR analysis. What we'll see, too, in a little bit here, is we're actually going to apply this into a cell layout. And we'll see why you don't want to spend all kinds of time whacking through your efficiency number when a by inspection solution is good enough. Because once you land that thing on the floor, all bets are off. Stuff starts getting in the way. So why would you spend all this time to be an efficiency expert if you haven't actually gone to Genba, if you haven't gone to the scene of the crime and see how things are flowing? The piece about the book is, again, it's well worn, it's hand tooled, it's the classic way of doing it. But unfortunately, the classic way of doing it is to some degree disconnected from reality. You can do the classic way at your desk. You can do the classic way in a conference room. And I'll tell you what, there ain't no manufacturing processes running in a conference room. That's why you have to go to Genba. So you want to spend as little time as possible futzing around with this stuff so you can take this piece of paper and get out into the cell and see how it executes. So here it is. The cell, I have the term there, project document. So you'll have this, right? It's unlikely it's going to be complicated, right? You'll likely basically have a single line with a single process steps marching across the page like that. That'll probably be your PQPR. Now, in the plant, if you're sharing pieces of equipment, then absolutely you're going to have part 1, part 2, part 3, and they're going to have a shared piece of equipment. Well, then show how these things interact. But if they're all 3 individual lines, this is a relatively straightforward process because really they're not going to play at all because they're not going to share processes. But if they do, then you'll want to run this process. Either way, you need to address this. You need to show a PQPR analysis. You need to show the process sequence, just like I have it here. Those are project docs that you need to provide. All right, those are project docs that you will need to provide. Okay, so we got our routing that we generated from all our wonderful work in the last 2 slides. And now we've gone to Genba. This is the actual cell. Ignore the letters right now. Just you walked into this room and that's where the process runs. And what you've learned is there's probably a better sequence of where to set these operations in the room you've been given. You've got some filing cabinets in the middle that are blocking the view and blocking traffic. But all you know is this is the cell you have, this is the location you have, and you're being given the opportunity to rearrange the deck chairs a little bit. So you go ahead and do that, and you lay your cell out from our previous slide, and it's R, B, E, F, A, C, D, S. Right? That's the best you can do, given what you presently knew until you've gone to Genba. So what I want you to do as part of this lecture is I want you to stop and take some time and step through parts number 1 through 5 and sort of follow them through with your finger and see where you have to go to make each one of those parts. Right? How the traffic actually flows. And this is important. And I'm calling it a project document because I'm going to want to see your overall cell layout. It'll be part of it could be part of your layout IQ, which it will be anyway. You also, for additional information as you're stepping through the PQPR process, you may wish to have a cell that looks like this from a spreadsheet. I'm cool with that, right? However you want to describe it. But you need to be able to show me an overhead cell layout of how your cell is absolutely running. I'm not going to prescribe which tool you use to do that, but I need to see that you've done it. And it's likely, probably, the easiest way to do it really will be with Layout IQ, because you got to do that anyway. So, what I want you to do is stop the presentation and march it. What you'll see is the effect of these filing cabinets getting in the way, the effect of backtracking. And what that begins to tell you is, well, in the classroom, in the conference room, at your desk, when you turn the crank on this, it was a great idea, but in reality, right, there's stuff in the way. What that forces you as a manufacturing engineer to do is to begin to reevaluate the floor itself, the things that are getting in the way of communication, right? The things that are getting in the way of effective walking routes. We call that cross traffic. This idea of having to have reversals and backtracking. Backtracking might not be bad unless your backtracking takes you from F back to B and you got to walk around a filing cabinet, right? Or maybe hey, your backtracking goes from D to E. I don't think there were any D to E's, but if there were, look at that distance, right? But so that's distance traveled. So all this is, I have the gold line here. This is the golden route, the 7 steps that no part follows exactly through, right? That was the 35, 7 times 5. This is the golden route, hence the gold color on the line. Reality will look different. Now finally we have here a cell layout from to chart. And actually this methodology sort of begins to approach what we'll be doing in Layout IQ in the lab that we'll go through in class. But you can see here for part number 1, right, they have systematically in this graphical form, this sort of quasi-graphical form, begun to lay out the part processes from R to A, right? Part number 1 goes from R to A, then it goes from A to B, another one in that box, right, from A to B, from to. The from is on the sort of the vertical axis, and the to is on the horizontal axis, right? And then you're going to go from B to D, so from B to D. There's a 1, part number 1. And what you could step through this, and what you can actually do, and this is not bad, this doesn't suck. You can As you begin to populate this with part 1, part 2, part 3, part 4, part 5, what you end up finding, remember before on the slide a few slides ago, I said, look, C to D, I think was 5 or 4, whatever tracks it was, and A to C was 4. I don't remember. I had enumerated. I had added them up, right? This is a way of doing that. It's almost like a heat map, right? It's like a heat map. And recognize, too, that above the line is sort of above the backbone, going forward. Below the line is a reversal. Below the line is a reversal. So this is not a bad way. In fact, I would encourage you to stop here, right? Make that graph-ish, plot these points, and look at the heat map for yourself. This is actually a really nice tool to help you with this really is a nice tool to help you with the PQPR. Because you look at this schmoz of a bunch of lines and a bunch of parts in a mixed model cell, and you put the blocks, it still may be kind of hard to see how things might line up. It's like another line of position. If you're like out in the middle of the ocean or you're on the coastline and you got to know where you are, and you want to be able to, well, this is before you had, satellite navigation, like I just look at a screen and it gives you latitude and longitude. You used to not be able to do that, okay? You used to have to, celestial navigation, navigational aids, dead reckoning. You had a bunch of different stuff, a bunch of different ways trying to help you figure out where you were. Right? That's sort of akin to that. Another tool to help you figure out where you are, because if you know where you are, you have an idea of how to get to where you want to go. I'm going to talk about this this process flow chart. The expectation is that you will have a manufacturing sequence chart, not a process flow chart in your project. That's the deliverable. I don't want to see a process flow chart. That's not what I'm asking for. I'm asking for a manufacturing sequence chart. But I know that many manufacturers, even here in town, are all goggle-eyed about process flow charts. So I want to make sure I go over it, because when you see this, you're going to say, oh, yeah, Professor Bona said that. Okay, so basically it's a diagrammatic methodology of being able to step through process routings by having symbols. So it's basic symbology and stepping through the process. On page 126, you'll find this table. You can see here that each one of these sort of situations has its own little diagrammatic symbol. If you memorize the symbols, then it's like a language. You can kind of sort out what's going on. Let's go ahead and see how this works in process. So here we see, I think this artwork comes from your book. I believe it does, but it might come from Suzaki. I forget. It doesn't matter. Either way, you see 3 products, and you see the process steps. Each one of these process steps, while they're not enumerated, right, they have a diagram, a symbol that it means something to somebody somewhere. In each one of these, then across the way, you have these shared operations. So it's a mixed model cell, perhaps for a mixed model layout, similar sort of idea, or it's a manufacturing flow through a plant, and you can see things stepping from operation to operation to operation. You can kind of diagrammatically see this, I guess. I struggle with this methodology, but that's maybe me. I'm feeble-minded, so maybe this speaks to you, and you go, I had a eureka moment. I totally get that. That's fine. The thing is, many companies use this methodology. What you see in the picture over here, the little graphic, is sort of a CAD representation of flow path. This is more akin to what we'll see in Layout IQ, where you're going to have process locations, right, operations, and you're going to see the flow of the parts through the operation. So on the left-hand side, it's kind of an old-style, classic way of representing parts flowing through a process. On the right-hand side is the new way of going from process operations, and you'll see that basically in a Layout IQ methodology. So here we have, this comes from Suzaki's work, and we have going back to almost this operation process focus. And what we see here is a shear and a brake and a punch press. And we have an assembly operation, there's sub-assemblies. What's interesting to note is there's lots of stuff going back and forth. These would be reversals, all right? These would be things that are going in the opposite direction. You could lay this out, again, as a PQPR. You could lay this out as your book does in that sequence, the from to diagram, all that stuff, right? the thing I want to leave you with you, the impression I want to leave with you, right, is you may be convinced that this is a appropriate process flow. But what I would say when I look at this is, holy crud, what's going on where? And the thing that jumps out at me most is this giant WIP table, work in process. Did I ever say WIP was work in process? I don't think it is. I just assumed you all knew what WIP was, work in process. So I apologize. WIP is WIP, and WIP is work in process. It's stuff that can't be sold. It's basically unusable inventory. It's putting work on a shelf that you can't do much with. It's useless. It's futile. It's muda. WIP is muda. So look at that big pile of muda. So let's go ahead and let the slide advance here. So now, interestingly enough, the assembly equipment stayed in the same spot. The warehouse stayed in the same spot. The sub-assembly and accessories stayed in the same spot. The pipe, whatever pipe operation, stayed in the same spot. We could justify having two shear operations. But now look at the flow. We talked about the flow analysis, the PQPR. Look what most of the parts now, we learned from our PQPR activity that most of the parts run from the shear to the punch press to the brake and then an assembly. So why not set our flow up to do that? A couple of WIP operations. This is likely because either the punch press has some changeover, so you have to build some WIP up in advance so that when the punch press is running, it runs like crazy and it burns the WIP off. It's likely what's going on there. And then you also have a brake press operation. Perhaps there's also some uptime issues. I don't know what the problems are, right? So you had to have some inventory between those process steps, which is never a good thing, but it's, compromise, right? So, but if you imagine the area of WIP being the quantity of WIP, we've knocked the heck out of it, right? Also, the process flow now is very much more straightforward. This is the sort of thing you folks will have to deal with. You're going to walk into a facility. Hopefully, when you walk in, you'll say, oh my word, what a nightmare, right? That's what you want. That's the fun piece, right? And you're going to use these tools to sort things out and make people's lives, basically, you're going to help make people's lives better. They're going to come to work feeling better because they can talk to each other. They can see what's going on. They're not buried in WIP. They're not walking futilely around. They're not digging through piles of stuff, trying to find where goes next. They're not suffering quality issues because they know it's from step A to step B to step F to step C, whatever it is, right? That's our job as manufacturing engineers, is to take a process that's sort of like what you see on the left and turn it into what you see on the right. These next series of slides, it says cell layout before improvement, and we're going to look at it before improvement. We're going to use that process flow methodology your book talks about, and we're going to kind of piece together how this whole thing kind of works. In this particular cell layout here, we have a milling machine, a grinding machine. We've got some carts and benches and tables and carts, and we know that carts and benches and tables equals what? Equals, everyone at once now, equals, oh, that's right, you're not here in front of me, equals WIP, work in process. Work in process is muda. But we see it anyway, all right? And I'm not going to go into super detail here, but let's go on to the next slide, which will show us in a somewhat granular way how this process runs. So here are our steps. And if you were to follow along with this, looking at that diagram I just showed you on the previous page, you would see this process as it flows from part to part. As a manufacturing engineer, this is why this methodology is liked by a number of manufacturing companies, is because you can annotate it as you're going through the steps. You have the diagram, you have the symbol, you can talk about it, give a little talk about it, and then annotate what you see. So when you go to Genba, it's not a bad way of going, is using this methodology. Taking it through step by step, what you see, categorizing it, right? And recognizing, in this particular case, look how much stuff's going on between milling operation and grinding operation, A and B. A and B are your money makers. That's where you're making your money. The rest of the stuff is waste. And it even says there, waste, 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 right? What you want to do is you want to have as little as possible between A and B. Let's go on to the next slide. Same story, right? Same story. Here's C, D, E, right? Look at all the crap in the way between C and D and E. Inspection, storage, and granted, right? Inspection is often important, but you're better off, right, making sure the process step itself in the first place made the part right, so you don't have to have inspection. Because inspection is waste. As a customer, I don't want to pay for you to inspect the part. I just expect the part to come to me right. Well, as an operator, why wouldn't I have the same requirements? Why wouldn't I expect the part to come to me right from the previous process? And you want to. So the question is, well, how do you manage that? Do you throw an inspector in there? Oh, Lord, just wrap dollar bills around stuff. You want stuff to go overseas? Do that. Waste your time doing that. You will never be competitive, right? You have to make sure that at the process itself, and you guys all know this, the operation is successful, right? And how do you do that? You eliminate WIP. You eliminate storage. You make sure the process is running properly. One-piece flow. So if a problem does occur, you can stop the line and fix it. Now, people would say, well, wait a minute, you have stop on the line. I mean, you'll never get any parts out the door. But it forces you. It forces you to fix the problem, right? It's to some degree, it's kind of cruel. It's like, nope, sorry, stop, fix. Well, yeah, stop and fix, and everyone's, high anxiety, lots of stress, too darn bad. Fix it, and then move on. That's the whole idea of TPS, right? This was one of Ono's teachings, right? One of his things he taught people. It was incredibly difficult for people to understand this. Why would you stop the line? Well, you stop the line to fix it. Yeah, but you never get parts out the door. Yeah, but eventually, you're right. You'll feel the pain today. You're going to flow like cream later. Fix the problems. Let's keep going. So here we have the before improvement, and as typical, as a stalwart manufacturing engineer, as a graduate of Ferris State University, these will be the things that you will consider. You want to look at the requirements of the operation itself. And storage, in our diagram we just took, right? We just diagrammed the whole thing. Storage is an operation. Absolutely, it's an operation. Is it needed? Is storage ever really needed? Material handling. Obviously, as little as possible. But if you have to do it well. But in this case, from a cart to a machine, to a bench, to a machine, to a table, to a machine, that's all material handling. You might be doing it really, really well, but it's all a waste. It's transport. It's muda. It's futility. Storage needs. WIP is bad. Eliminate storage. Period. Period. We talked about inspection already. Don't pass on bad product. That's how you solve that problem. Make sure the equipment's running properly. Delay reasons. So again, we talked about why you might have WIP. You might have WIP because the machine runs like crazy, then it has to be changed over, or it stops, or it locks up, or blah, 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 right? These reasons of delay increase the time to get parts out the door, so your cell cycle is damaged, right? The morale of your folks on the line is damaged. Parts sitting in WIP will likely get lost or damaged, right? It's all those things. It's muda. Eliminate muda. Combine operations, or better still, obviously eliminate operations. You think about overprocessing, right? Overprocessing is the worst of all. I'm not sure I said that in class before, but it is. This is the worst of all the muda sins. Why? Because you're taking time to put more effort into it, right? You have the risk of ruining a part when you're doing overprocessing. You're spending the time on the equipment that you had to pay for to be there. You had an operator running it, so they're not doing something important because they're I think it hits almost all of the 8 wastes. Well, I guess 7, because one of overprocessing is one of the wastes. You get the math, all right? And finally, when you look at this, right? Let's say you had 2 operators. You'd have to have more than 2. Let's say you have 2 operators in this line. When they go to push that cart out, what do they got to do? They got to walk back to where? Spot A? Let's look at this in some detail, shall we? So, again, I got my little mental ink at the top there, supposed to be counterclockwise. Mr. Suzaki has once again let me down. I can't explain it. It's just what it is. Beat a dead horse. So just assume these are all going counterclockwise, right? The I-shaped line is essentially the line we just saw. And it's what I just talked about. When you finish it, you got to walk all the way back, right? Now, you may have some space constraints, right? And you may have no choice, and that's the way the line has to look, and fine. But I have found typically it doesn't have to look that way. When you have an I-shaped line, except for like a vehicle assembly plant, okay, it represents a total loss of creativity. It's a land of what the heck, I'll just make it straight and throw a bunch of people at it, right? That's not how you make money, folks. The L-shaped line is a step in the right direction, but the U-shaped line is the way you want to go. In and out, especially because you want to be able to flex your manpower with the demands on the line. As the tack time, the demand, we talked about tack time, as the tack time increases, follow me on this, right? When tack time increases, that means you have more time between parts, or more time to make the parts, because the demand has dropped. So as the tack time goes up, which means demand goes down, you want to be able to match the cycle time to the tack time. We said that a couple weeks ago, right? So how do you match the cycle time with the tack time? Well, first and foremost, you don't automate everything. Right? You have a lot of manual operations and quick, fast hit manual operations. And number two, right? You can flex the manpower. You can have a cell that runs with one person. You can use that person someplace else in the facility where the demand is higher, because hopefully your manufacturing plant isn't just a snow shovel plant, right? So when you can flex your manpower, and that's why you have flex manpower, that's why you cross-train, so that you can expand your muscles when you need to in a cell by putting 2 or 3 people in there to really make that thing run to meet demand. And when your Kanban is full and your finished goods inventory is full, and you're not getting pull signals anymore, your pacing operation, the pitch of the cell based on pallet pulls is gone quiet, then you can have one person in the line run as needed, maybe 2 hours a day to kind of fill the finished goods inventory. That's why you want to have a U-shaped cell. So you can have 1, 2, or 3 people in that cell. Okay, Project Doc. Okay, once again, it's going in the wrong direction. You got the mental ink up there. What we see here now is a cell with one operator on it. It's a U-shaped cell. And it's going from A to B to C to D. We're going to diagram this in a second with the same methodology we diagrammed it before, trying to pull stuff out from between the process operations. All the stuff in the middle was non-value added. But you can see here that the cell in an overhead view, right, is capable now of being able to manage itself based on the requirements, based on tack time. If the volume is dependent upon the cycle time of the machines, right, I could have an operator at A, B, C, D, and E, right? I could even have a person at F moving the material. If it was a one-piece flow, I could be humping this cell, man. There's nothing that keeps me from running this cell like crazy, right? If I'm stuck with heavy automation, there's nothing I can do about it. I got to have 2 people there. It doesn't matter, because it's like, well, 25 parts got to go in, 25 parts got to go out. But if it's one-piece flow, I can fly in this cell. I can dial it back with 1 operator, or I can absolutely fly with 5. And what that means is no overtime. I flex my manpower, I run it on a day shift, I run it for 8 hours, and everyone's going home at night to see Mama and Papa, right? That's the way you want to run a cell, a cellular environment. Project Doc, so we talked about it before. Likely you'll use Layout IQ, but I need to see each one of your individual product lines with an overhead view of what's going on and why you got there with it. So again, process flow chart, the methodology I'm not asking you for, but many companies do. We'll step through it real quick here. You can see in general now what was a 2-page operation, right, just became a 1-piece flow production line. And they've close coupled then each one of those process steps in a 1-piece flow environment. I'm not saying you can do that all the time. But what I'm telling you is, if you want to make money, if you want to have a vibrant workforce, you want to have happy people pumping stuff out, you want to have well cross-trained employees, this is the way you set up a cell. This is how you make money. Now, as part of Layout IQ and part of your overall facility design, we've looked at cells, right? And we looked at traffic within the cell, that U-shaped traffic, right? We talked about some of that. But then those are the individual product, lines that each of you will be responsible for in the cell. But you take a step back. Your manufacturing facility itself also has traffic patterns. Part of Layout IQ, you're going to have your cells plugged in the plant, but you're also going to have the overall facility plan. And in that, you also need to look at traffic patterns of your people. Who's going where? Because it helps you figure out where to put the bathrooms, where to put the offices, where to put the QC lab, where to put the parking lot, all that stuff, right? I mean, recognizing that the paths your employees take aren't just in the cell. It's from the lunchroom to the floor to the potty to the cell. You have to look at those during the course of the day, right? When folks drive to work, they got to park their cars to get it from the parking lot. When they enter the building, they got to figure out where they're going to punch their time cards. How many time card spots? You're going to have one for the whole facility? Well, if it's a tiny facility, yeah. But if it's a big one, you got a bottleneck of a bunch of people waiting to punch through. You don't want that, right? They go to their lockers, they go to the cafeteria, they go to their workstation. You have to think about the cell, the flow, not only in the cell, but in terms of the entire manufacturing facility. What else do I want to say on this? I guess that's about it, right? So when you think about you're focused directly on your manufacturing cell, and I get that, and you got to be. But folks, this is more than that. This is a manufacturing facilities planning class. You are designing and planning an entire facility. How your people flow in the cell also has to be well understood, well documented, and presented as part of your project. So some final cell thoughts, cell layout thoughts. And these are the questions I want to leave you guys with, you folks with, as you not only do your project, but also as you kind of go forward in life. You always want to ask if there are operations I can eliminate. And you have to do that in a way, don't think about the people, right? Think about the operation. You want to have people, working at positions and operations that are meaningful. Folks know on the manufacturing floor if they're doing something that's not meaningful, right? It's like you're filling a hole, you're digging a hole and filling a hole. What I do all day long is I dig a hole and fill a hole. That's what you do to people. That's what you do to prisoners. It's not, that's not what you do to your employees in your facility, right? You want employees in the facility to feel valued, and they feel valued when they are working at valuable operations. You have to ask yourself, will automation help or hinder? And when I say hinder, does it lock you into a cycle time? And locking you into a cycle time also locks you into a manpower planning requirement in a particular cell because how that automation runs. Automation isn't always a good thing. And I know you're in automation class, and you have to have automation in the line. I get that. It's part of the deal. I understand. All I'm saying is be cognizant of the fact that operations that are automated aren't always the right choice. You want to ask yourselves, too, when you look at these operations, are they really separate operations? I mean, we went and we laid all the steps out, and we had the diagram and the PQPR, but you have to ask the more fundamental question, right? Process D and E, machining operation 1 and machining operation 2. One's running on a lathe and one's running on a mill. Okay, but maybe they could both run in the mill. Because if they're both running in the mill, I mean, it's a piece of equipment I don't need. But secondly, maybe I can interpolate that circle. I don't have to run it in a lathe. I'm not going to block it up and lock it into a spindle and spin the darn thing. I can go and there's enough math and enough precision, and the tolerancing is such that actually, if I interpolate that diameter, I am good enough. Let's get rid of the lathe. 1 mill operation. Yeah, it's going to cost me some cycle time. It might cost me some cycle time, but it's the door-to-door cycle in the cell that just got improved. All right, enough said there. Can I change the routing to reduce distance travel? We've hit that one like a bazillion times, but it's an important question to ask. Can I move workstations closer together? Absolutely, yes. Look at that little beauty right there on the page. We did that. Well, we didn't really do it, but we could do that, right? Can I justify production aids to the increase of effectiveness? What is a production aid? A production aid is something that's going to help an operator grab with the right hand and place it in a nest, right? What's going to help the operator be successful with that? How do you manage that? Maybe the production aid is a piece of equipment that actually picks up an engine block for the operator. So they're not lifting it. Obviously, you're not going to lift an engine block. If you're an anvil manufacturer, you're not going to ask your operator to lift the man. But that's a production aid. Something that, like maybe instead of bending over and wrenching on something, you've got a table that comes up, lifts it up so it's at the operator's eye level. Right? And so you're going to spend some money on this lift device. And obviously, you don't want to have it be a dangerous lift device when it drops and somebody's foot's in the way. You got to think about that. But does this lifting of the device or having the process operation at table level, does this improve? It will improve throughput. Absolutely. It'll also help operator morale. Those sorts of questions have to be asked. And finally, how much does this part cost to produce? And this is the tough question. And it's kind of like, what do we want to be? What do we want our company to be? And maybe we want our company to be vertically integrated, right? Because when we're vertically integrated, we can be agile. But is the company willing to pay for that? If you're not super good at it, we talked about that in the first night. If you're not super good at something and it's not your forte and you're spending a lot of time and effort at it, maybe there are other people that can do it better. They're not necessarily, across the Pacific, right? Maybe there's somebody locally that can do it better. But you can close couple, and you can have daily shipments and on-time delivery between you and the other shipment, right? So maybe you can work that in and help improve product quality and get rid of a process and operation that's not really working well and costing a lot of money. That's always a possibility. As a manufacturing engineer, we have to ask that kind of question. So here's a standard worksheet. The standard worksheet is a project doc. This is a required project doc. And I want to take a moment and step you through this. So in this particular case, I have an operation, right? I have two operators. I have counterclockwise flow in the cell. I can only see the arrows and the directions, but believe me, I do. All right. And what you see here in this is an actual document. I believe I will have a copy of this. If I don't, it's easy for you to make. It's an Excel spreadsheet document. It's easy. But I think it is part of one of the spreadsheets I'm handing out. You can see in this standard worksheet, two operator layout, right? You can see all of the safety points where there's a safety precaution area. Remember, plus QDIP, right? You can see where quality checks are. The quality check isn't necessarily somebody walking in and taking a scale to it and saying, oh, congratulations, right? There's a process step and then something that's going to verify it before it leaves the station. Before that part leaves the station and goes to the next operation, which is sort of the next customer, you know that it's going to be sufficiently capable of meeting requirements. You can also see where standard whip locations are. And yep, there's whip in every spot. You say, Professor Bono, why is there whip in every spot? In this particular case, we're wetting the line. And I'd ask right now, if you were all you bright-eyed and bushy-tailed standing in front of me, and I'd say, how many of you have ever heard of wetting the line? What does wetting the line mean? Anybody know? Some of you might. So when you walk into a cell, right, every operation has a part ready to go to start that operation. If you were to walk in a cell and had no parts in the cell, it was completely cleaned out, right? Operator 2, operator 1, let's say operator 2, the orange guy there, operator 2, right, starts. And he starts with the drill press. And then he goes over and he or she, this person, okay, this individual, then goes to process 2, does a drill, and then does a counterbore, and then reams some. What's operator 1 doing right now? Nothing. Operator 1 is sitting there doing nothing. Well, that's a waste. That's an absolute waste. So, this single piece of whip is kind of like a tax, right? Yes, it is waste-ish, because I've been hammering on whip, and whip is waste. It's one part. But this one part, when you walk in, every operation is started and running, right? Because right now, if there's no whip in there, Operator 2 has to sit there and wait for the holes to drill, right? Before it, assume there's like an auto eject, right? You got to wait for it to auto eject before you can go into the next operation. But if every operation has a part that's already ready and primed, operator 2 can run the rabbit run, right? He can put the part in, hit start, walk over, hit the next part in, start, boom, pick apart, pick them up, all the way around the cell, right? Cell's up and running immediately, right? Operator 1 is already up and running and ready to put stuff in the pack box. That's called wetting the line with one piece of whip. So yes, I have a whip location in every process step in the cell. Bad me, but no, not bad, good me, because I can run the cell right away. So it says right there, pieces of whip. So I am planting the flag, wonk, 5. Down there at the bottom of the page, there's pieces of whip, you see that? I have planted the flag, wonk. I am telling you right up front, I am having 5 pieces of whip. Why? Because I like you, and I want you to work right when you come into work, and those 5 pieces of whip are wetting the line. You can also see tack time, right? 62 seconds. The customer is pulling one every 62 seconds. And you can see right now the cell cycle is 35.5. So you say, well, golly, why do I have 2 operators in there? Well, I have to, right? Because the tag time is 62, my cycle time is 35.5. If I had 1 operator in there, I'd fall behind. So I have to run this shift, or I have to run a split shift of sorts, where I man the cell just because of how it all lays out. I have to have 2 operators in there, but they won't be in there for all day. They'll be in there long enough to meet the demand based on the pitch of the outgoing pack out. That's what they have to be able to manage it to. So they will run the cell for a partial amount of time. If the cycle time was exactly 31 minutes, if I do this right, then it would be actually a cycle with 1 operator would be 62 seconds. I'm sorry, did I say minutes? Bad me, seconds. Seconds. If the cycle time was in quantities of 62, let's say it was a 31-second cycle time, which would mean for 2 people, with a 1-person playbook, it is a 62-second cycle time, then my cycle time meets tack time and 1 person can be in the cell. But rarely does it work that way. It can, but rarely. So in this case, I have to have 2 people in the cell. Now, this is a project doc. You will have a standard worksheet as part of your project for each of your lines. And if you've got 2 or 3 cells in your manufacturing line, you will have 2 or 3 standard worksheets for your manufacturing line covering that line from the cells. Now here, I'll pop in. Here's a pop in. Where'd my pop in go? There it is. Right. So here then is the standard work combination sheet. And if you look closely at the standard work combination sheet, each of those process steps are shown there. I have 2 operators. I have my cell cycle for 2 operators. I have my tack time requirements from the customer. I have each of my process steps logged in there. So yeah, I do have a process flow, but it's in the standard work combination sheet. I have my manual time, my automatic time, my walk time, all that stuff's in there. Some of these numbers you guys are going to have to make up because you don't have walk times. You're going to look at your cell layout and decide how long it's going to take to walk, and that's the number you're going to use. Your automation class, if there's an automation piece of equipment, you know what the cycle time is for the automation equipment. But if it's a manual operation, this is the whole table time thing we've talked about. You'll have to construct your table time. You'll have to construct your table time to manage that. Finally, what else I have here? That's the manual machine walk. Yeah, that's it. So you'll have this as part of your deliverables in your project. This spreadsheet you will also get from me. This is what we'll give you, and I think we actually work on this one in a couple of lectures when we go through it in grave detail. All right, so that's that. Let's talk briefly about Chapter 15. And we've got this is our simulation chapter. This is really an introduction. The lab, the Layout IQ lab is where we really sink our teeth into this. But I want to introduce the idea of simulation. It's a chapter in our book. It's 16 chapters, 16 weeks. And we got some weeks where we've got a midterm. We got some weeks where we're traveling to plant visits. So some weeks we're going to do 2 chapters. There you go. understand concepts of simulation, basic models, software program, and to be able to apply simulation to evaluate layouts and material flow. All right, moving on. So you've planned, you've drawn, you've schemed, and yet somehow, some way, you've ended up with blunders. Somehow you had insufficient space to hold in-process inventory, or you had mismatches in machine capacities, or ineffective, inefficient material flow, or I don't know, maybe bottlenecks sort of cropped up, miscalculations in ROI, return on investment, by the way, of your investment of your equipment, for a particular piece of equipment for a machine. People are bent out of shape about that. Maybe you've got some congested paths. You've got some interaction between two different cells where people are walking, or they're walking to do a process, but it also happens to be the place where everyone walks through to go potty. You know, who knows, right? Maybe there's a problem with fork trucks getting around, or you've not left enough room for a stretcher, right? And the health and safety folk, HR, came out and looked at the cell and says, how the heck am I going to get anybody out of here? They're like locked in, right? The list goes on and on. Simulation, especially layout IQ and tools like that, can to some degree help you discover these blunders before they rear their ugly head. So simulation can resolve these mentioned before, blunders. They can help you generate some very complex models depending on the level of the software. Layout IQ is not a high level. I mean, it's decent for what it does. It's for us students, right? It's not going to give you a super complex model, but they're out there. They exist, right? And also the thing about a lot of the simulation models that are out there, they're likely expensive, they're very time consuming, but they can give you tremendous insight in the manufacturing facility. So typically what happens though is the response to these complex and expensive modeling efforts, owners and manufacturing facilities and the like, they tend to go to a quick and dirty estimate. And the problem is, quick and dirty may not reflect all of the essential facts, because if you're quick, there's the quick and the dead. So there are quick and dirty risks, beyond the quick and the dead. Quick and dirty disadvantages don't generate optimal solutions. They generate results based only on the model that you presented for analysis. So the garbage in equals garbage out, right? So really, you have to really kind of watch it when you're using simulation tools. And you have to sort of balance the effort you're putting into it, the results you want. And you're trying to find, in general, the best solution. It kind of almost goes back to that previous thing where we did the efficiency number of our layout. Well, okay, you can calculate an efficiency number, but beware, right? When you go to Genba, when you go to the scene of the crime, when you're there looking around and you have situational awareness, things aren't always as they seem, right? So these quick and dirty trial and error approaches, they're not bad, right? And they can produce different results, though, in repeated runs that may lead you to, interpretation, error, opinions, right? The thing is, right, is that you'll need them anyway. So, it's quick and dirty and it's likely to get used and design and give you some access, a visibility of the issues, right? You have to be aware enough of what the garbage went into the analysis in the first place, right? I am not necessarily averse to quick and dirty. I'm not. The PQPR is quick and dirty, right? The thing is, it's like how much time and effort versus you have to put into it. Over processing is a waste, right? Versus understanding what's going on and going out there half-cocked, right? Those are two sort of ends of it. So you have to sort of balance it. Yeah, sometimes though you really have no choice. You have to spend more time maybe than you want, but you can't look away from it and say, quick and dirty is not. No, you have to balance that. You have to use your brain. Layout IQ, right? There's a picture of it here, right? Is kind of quick and dirty. It's okay. It is sufficient enough for our purposes for what we're doing. This will not be a life choice for you, all right? Though you may so much enjoy working with the software that you'd like to be a consultant someday doing these sorts of things with high-level software and meeting with customers and doing customer plans, and that's a completely decent. Decent, not the right word. It's a viable option. It's a completely viable option as a manufacturing engineer, right? To be part of a consulting consortium and do this kind of work. Layout IQ is maybe a first step in that regard. It's going to give us the ability to assess and analyze our manufacturing facility to enough of a degree that you're getting a taste of it. All you're doing is getting a taste of it, right? But you're also, as part of the team, showing me that you've gotten that taste. Part of the garbage in, garbage out we talked about is what you have to do to load data into Layout IQ. So you can see here there's sort of the box in the bottom down there. You have to structure your spreadsheet. It's the data you're going to load into Layout IQ, and you guys are all going to do tutorial 1 at home, right? And then we'll have an in-class tutorial. But in tutorial 1, you do load a spreadsheet in, right? And the spreadsheet has this layout, and it's sort of the process of getting information into Layout IQ requires you to build a spreadsheet, and it's a spreadsheet that is a kind of a from-to spreadsheet. And you can see, we talked about it previously, right? In that slide ever so long ago, we had that sort of that graph with a diagonal line. Well, this is that graph. You can see sort of in the picture there, you see that diagonal line running up. Right? It's going in the opposite direction, but it's the gray boxes are that diagonal line, right? And you have storage, and you're going to have receiving, and so you're going to have all the same kind of elements we saw in the classic methodology, but they're replicated here. And we talk about this Excel spreadsheet. It has to look just like this. We'll talk about that in class, but you're going to have the product name and the part name, right? So the product name is and I think we'll go through this in detail, but I want to talk through it right now anyway. Let's just keep going, right? The product name is one of the products you're going to be pumping out, right? You may have some parts that are part of that product, right? The flow factor is, let's say you have a manufacturing line, and it's in this manufacturing line is making 3 different parts, or there's a part that's leaving this process and it's going to 3 other processes. Maybe it go, and that's that backbone we saw, right, where we had 5 parts and they didn't all go the same way. Maybe they all went through process A, right? But when they go to the next step, some go to process B, some go to process C, and some go to process D. The flow factor is the percentage of parts that go to process step A, or excuse me, okay, it came from A, there we go. It's going to, the percentage of parts that go to process B and C and D. So maybe it's like 70, 20, 10. So 0.7, 70 of the parts go to the process step B, right? 0.2, 20% go to process C, and 0.1, 10% go to process D. That flow factor helps the software figure out how much of a load is going to this next step in the process, from and to. The device name, interestingly enough, is the device that makes the transfer of the parts. So there may be no piece of equipment. It's a one-piece flow. It goes from this step to that step. All right, well, it's probably in a cell. Probably won't even use Layout IQ within a cell, but you will, because you're going to play with it. You're going to show how it works, and why not use this? Why not use Layout IQ to show that? You absolutely can. You don't have to, but you can. It's one way of doing it, right? The device name, though, might be a fork truck, and the unit load might be there's 500 pieces. So as it goes, sort of, it's the lot size that runs from that piece of equipment. From the from to, right? When it's at, how do you get there? What quantity is going from and to? Well, getting from to requires a forklift. That's the device name. From to could be a conveyor. From to could be, operator A, right? And the unit load is how many parts. Well, if it's a one-piece cell, right? The device name is operator A, and the unit load is 1. if it's in a cell, one-piece flow, operator and unit. Device name. Operator is the device and unit load is one piece. However, if it's coming out of let's say a machining operation with a bunch of palletization going on, and you got to pick all these things up and send them across the plant, well, the device name at this point is forklift, and the unit load could be 50 or 20, right? Because you're taking a lot and you're zipping it across the plant. That's your unit load. So that's the structure of the spreadsheet that you're going to dump the information into. It always has to look this way. You won't actually have the names in the spreadsheet. We'll learn that in class, but you'll have to have the data in there so Layout IQ can suck it in. So here we see this is from tutorial 1 that you'll all run at home. You can see Loretta was the product name and the part name. Loretta's a nurse, right? Loretta is a nurse. Everything she does 100%. So she goes 100% from R26 to R35. Those are room numbers. Those are room numbers on a hospital floor. And then the device name, well, we haven't called Loretta a device, and she probably appreciates that. And the unit load is 1 because it's her going from spot A to spot B, herself, and her. So, and you see here then Layout IQ, before the paths have been corrected, this is like just the direct, I think it's called Euclidean distance from point A to point B. Obviously, she's not going to walk through walls unless she's a ghost. And at that point, we'll have a moment of silence for Loretta. But Loretta's not a ghost. She's a real nurse, and she's walking the halls, so you have to correct the paths. But anyway, you can see that the sort of the network that she's following. This is the beginning of putting in your layout, your process. So you're going to have your manufacturing lines, but you're also going to have an overlay, if you will, of your people flow, change of shift, how they're getting to the bathroom, how they're getting to the parked cars, how they're getting to the office, all that stuff. You have the ability to show all of those things with Layout IQ. Okay, mercifully, because you know what, my voice is getting a little dry here. And hopefully your ears are not too tired. Call to action. Call to action, lecture 3. So you're going to focus on a product-focused facility, not process. Unless you say, Professor Bana, in this particular case, because of how these 3 manufacturing lines pumping out 3 different products are interacting, we have a shared paint booth. All right, shared paint booth. You just became, in that specific case, kind of a product processed focused operation. I'm cool with that. That's groovy. But in general, you're product focused. Manufacturing sequence chart, required document. Cell layouts, always. And I say almost always. So yeah, it's like everything, rules can be broken. Sometimes you may find that because of whatever, a counterclockwise layout isn't exactly going to work for you. I have an actual example. I would diagram it on the board in class if we were there. But imagine, if you will, 2 sides of an operation, right? And it just so happens they were mirrored operations. They made 2 very, very similar products, but because of how the products were made and the requirements, they had to have different test equipment, they had to have different components. They couldn't, and the volume was such that both of these cells, if you will, had to be manned pretty much fully to be able to manage takt time with cycle. Right? But these 2 products then often were sold together. They were like a matched set. So in that case, they both flowed together, and then they pooped out the back of the line, right, in the pack box as a matched set. In that particular case, because the operations were almost mirror images of each other, one ran clockwise and one ran counterclockwise. It's just the way it worked out. It's rare, but sometimes it happens. So cell layouts almost always counterclockwise. PQPR, we went about that in grave detail. Know it, live it, love it. Cell layouts to be considered a standard worksheet. Yes, your cell layouts will be described as a standard worksheet, one for each product. And then, of course, we went over Layout IQ Intro, and we'll do more of that in the lab and class. All right, folks, that's it. Wrapping it up. Hope you've enjoyed this as much as I have, talking to myself in my office. Yeah, you know. Anyway, it goes to the territory, people. It goes to the territory. Hey, we'll see you in class. Have a great week.